this video, we will be looking at integration, and specifically with volumes of solids of revolution. And we're going to demonstrate the proof for the volume of a sphere. So starting with the equation given, so y equals root r squared minus x squared, we're going to use calculus to prove the volume of a sphere with radius r as seen. And I have here a few examples that I'll just demonstrate before we do this. Of course, you need to have a little bit of grounding in integration already. So if you're in grade 11, you will know definite and indefinite integration, and you'll understand how that works. We'll start with y is equal to r squared minus x squared. Where does this come from? Just to make it clear, the equation of a circle in its basic form is x squared plus y squared equals r squared. And when you rearrange that, you will cancel x squared on both sides and bring it over. So you'd have r squared minus x squared, and then of course your square on both sides becomes the square root when you cancel it on both sides. So what we're dealing with here is only one version of this now. We're going to look at the top half of our sphere because we just want to see the positive answer. So there's obviously a full circle, a full sphere, and it would be the top half is the positive answer, and the negative answer would be the bottom half. Okay, let's have a look at a few examples before we start. So if I were to just draw in a few rectangles and stuff here, we have what seems to be a rectangle, but actually when you're looking at questions, you'll be looking at a 360 revolution of this. So we'll bring another shape down below it of the same magnitude. And what this actually is, do it in green, is a cylinder. So you can deal with cylindrical shells and washers and discs. And sometimes you could use both, or you could just pick the easier version. You'll get used to that as you practice these. And the same with this next one. So we have a rectangle again, but it's not actually on, we'll say, the x-axis. It's above it. So what's actually happening here? If I just draw another one, and we do the same thing again, you'll see that it is the same idea. We have a cylinder, but it has a hole in the center. So that would be like a washer. So for instance, you'd find the volume and take it away from the volume of the hole, let's say. And that's the idea, if you see that kind of picture or diagram. Next one, maybe you can guess. I'll just draw this one out. The next one is a cone, okay? So with a cone, of course, you won't see a cone per se, but you kind of have to just wrap your head around the fact that it would be a 3D shape from the types of questions you'll get. And so on. You may get irregular looking shapes. You might get kind of shapes that look like a vase, something like that. And that's about the extent that you'll get in grade 11, those kinds of questions. Now we're going to look at the proof. So, definite integration. So V for volume. So the volume, so this is the integration sign. So B and A are our limits from the right to the left. The distance of the shape on the x-axis, we'll say, or y-axis. But for now, we'll just do one of these. We have pi y squared, and of course dx. So we're always with dx, with integration. It's like we're chopping it up, we're splitting up, we're dividing the shape into different slabs. And this formula, of course, could be another proof. But think of it similarly to the way you would look at volume in GCSE even. You have the cross-sectional area And you may have a height or a length depending on how the shape is standing. And it's pretty much the same idea. Pi, of course, is synonymous with circles. Okay, let's get started. Now, back to our pictures a little briefly. We have r and minus r is our diameter, but the radius is there. Okay? So our limits are r and minus r. So we plug in pi, and then our y was already given to us. Our y is root r squared minus x squared. That's given. So we plug that in. R squared minus x squared, and of course that is all squared. And we simply from there we simplify, I suppose, the things. I can do it all the steps though, I suppose. So our square and our root cancel out. So we're left with r squared minus x squared dx, of course. Oh, I should always put that in. Always put that in there. V then, breaking it up. So I'm going to move to the next step with integration. Pi. So I'll just rewrite it, but I'm going to integrate it now. So with integration, we go one extra power, so r squared or r cubed. So you're thinking to yourself, would that be correct? Well, actually, scrub that. Actually, that doesn't change. That stays the same, because the x or the y in the case of doing integration is a variable, and that changes, but r is a constant, so that doesn't change. So leave that as it is. Don't change that to r cubed or 1/3 r cubed or anything like that. So obviously 1 becomes x minus, and then 1/3 x cubed. Again, you have to know definite integration to have this set out. And we put our limits there at the end. And from there, you can subtract one from the other. So we leave pi for now out front, and we'll do that out. R squared and x. X, in this case, is our limit of r. So we put that in. Minus 1/3 r cubed. Now, I'm going to put separation over these. Subtracting both. So again, do the same thing, but this time I have minus r as my limit. And put your brackets and everything, because you want to make sure you don't make a little error like that with those. So minus r again. Okay. And from there, multiply it out. Pi. R squared times r is r cubed. So r cubed minus 1/3 r cubed minus. So minus times a minus. Be careful, we're not doing that yet. So we end up with minus r cubed plus 1/3 r cubed. This one is minus times a minus. That's within the brackets. So just be careful there. Minus times a minus is a plus there. And nearly there. You can simplify that down again. So r cubed minus 1/3 r cubed is 2/3 r cubed minus, again, do the same thing again. I'm just going to do minus times a minus is a plus. And so you'll end up with the same. In this case, a different sign. And of course, if you just check it there. Actually, just a minus, not a plus there. Of course, that was a minus there. If you just put that all together, this last step, you'll end up with pi, and 2/3 r cubed plus 2/3 r cubed is 4/3 r cubed. And that's the formula for a sphere. It's rewritten. It's commutative, so you can put the variables in any place, or constants in any place you want. So 4/3 pi r cubed. And that, I'll just rewrite, just so it looks like the original that we had above. And an interesting case, actually, is that the area of a circle is the derivative of its perimeter or circumference, and same with a sphere, the surface area is the derivative of its volume. It needs a little bit more explanation, but it doesn't work for some shapes like the ellipse. So it's to do with parametrics. It works with the fact that we're using radius as our constant. It doesn't quite work with diameter, for instance. But to look into that yourself, to see how that works with integrals and derivatives, would be an interesting side project. And that was the proof for the volume of a sphere for grade 11 integration.